Graph Theory Class 11 Video 2. In this video we're going to look at another application of colouring graphs. We're going to look at scheduling problems. And this might be a bit of a surprise application, like how does colouring graphs, how could that possibly apply to scheduling problems? But we'll see in this video how it actually applies. So the general setup, what's the general situation that we'll be interested in? So there are multiple different events that need to occur, and exactly what the events are isn't too important. So they could be like meetings, classes, exams, like committee meetings, anything like this. There are just different events that need to occur, and there's more than one of them, okay? And in general, more than one event can occur at the same time. Like you can have more than one exam happening at the same time, but some events have conflicts, okay? So the classic conflict could be that the same person needs to attend multiple events. So you can't schedule two events for the same time if there's a person that needs to be at both of them. Okay, I think maybe the most intuitive example is probably exams. Like multiple exams happen at the same time, but you don't want to need to be in more than one exam at the same time. So the university tries to schedule it so that you don't have exam conflicts. It doesn't always succeed, but like the university tries to schedule it so you don't have exam conflicts. And the question which you try to answer is, what's the minimum number of time slots needed so that you can host all of the events? Okay? I mean, obviously, if you just host every event at a different time, then yeah, there's no conflicts and there's nothing to worry about. But that's not very efficient. I mean, imagine if like the university only ran one exam at a time for every single course in the whole university. If there was just one exam at a time, then exam period would be like half a semester long. Okay? But it's not. It's a week long, and it's because multiple exams happen at the same time. So how do we solve this type of problem with graph theory? This is the general way to solve it. Okay? The first thing you do is you draw a conflict graph. And this is just a graph where the vertices represent the events. So like the different exams, there'll be a different vertex for each exam. Or the different committee meetings, there'll be a different vertex for each committee meeting. And you draw an edge between two vertices if they're in conflict. So you draw an edge if the two events represented by the vertices cannot happen at the same time. So it's a conflict graph. It represents the conflicts between the events. And then you find the next step in this operation is you find a minimal colouring of the graph. Okay, so you've taken your scheduling problem, you turn it into a graph, then you find a minimum colouring of that graph, and then the final step is just for each of the colours you used, you let it represent a time slot. Okay, and by the way that we constructed the graph, this means that none of these time slots will be in conflict. So let's just do an example and see how it goes. So here's an example. There are 8 people: Alice, Bob, Charles, David, Eve, Frank, and Grace. Okay, and I'll just call them A, B, C, D, E, F, G. And there are 7 committees. So here are the committees right here. Committee 1 consists of Alice, Bob, and Charles. So that means that Committee 1, to meet, they need Alice, Bob, and Charles there. Committee 2 consists of Charles, David, and Eve. Committee 3 is David and Frank, and so on and so on and so on. Okay? So the first thing we do is we draw a conflict graph. We draw a conflict graph. So I need to draw a graph with 7 vertices which is readable. So what do I have? 1, 2, 3, 4, 5, 6, 7. Okay? And the vertices represent the events, and the events are the committees. Okay, so C4, C5, C6, C7. So the vertices represent the committees, and then there are edges if there is a conflict. So how do I work out if there's a conflict? Well, there's a conflict if any given person needs to be in both committees at the same time. So for example, Committee 1 and Committee 2, there's a conflict because Charles needs to be in both of them. So that means I draw a line like this. That means I draw a line like this. Okay? Because Charles needs to be in both of these committees. So C1 and C3, is there a conflict? There's no conflict. There's no overlap in the participants. C1 and C4, well, now there is a conflict. So I draw a line. C1 and C5, there's no overlap, no conflict. C1 and C6, Bob needs to be in both. So that's a conflict, so I draw a line. C1 and C7, Charles needs to be in both. That's a conflict, I draw a line. Okay? And I need to do this for all of the committees. So now let's examine Committee 2. So C2 and C3, David is in both. So that's a line I draw there. C2 and C4, there's no conflict. C2 and C5, Eve needs to be in both. So C2 and C5, that's a conflict. C2 and C6, Eve needs to be in both. So that's a conflict between C2 and C6. And finally, C2 and C7, Charles needs to be in both. So that's a conflict. Okay? This takes a while, but it's unavoidable. So let's move on to C3. 3 and 4, no conflict. 3 and 5, no conflict. 3 and 6, no conflict. 3 and 7, Frank needs to be in both. So there's a conflict between 3 and 7. Okay? 4 and 5, no conflict. 4 and 6, Grace needs to be in both. So that's a conflict. 4 and 7, no conflict. 5 and 6, Eve needs to be in both. So that's a conflict. 5 and 7, Harriet needs to be in both. So that's a conflict. So 5 and 7, like that. Okay. Finally, 6 and 7, no conflict. Okay, so here's my completed conflict graph. Now I just need to find a minimal coloring of this. Okay, and that's easier said than done, but let's give it a try. Well, I'm just going to color them with the colors T1, T2, T3, T4, and so on. T stands for time slot 1, time slot 2. So I might as well color this T1. C2, I can't color it T1, so I'll color it T2. C3, I might as well color this T1. C4, I'll color it T2. C5, I will color this T1 again. C6, I can't color it T1 or T2, I'll color it T3. And finally C7, I can color this T3. I'll color it T3. Okay. So this is a 3 coloring. And is this the best I can do? Well, yeah, it's the best I can do because I can see this, which is a clique of size 3, which means that the chromatic number is at least 3. And I found a coloring with 3 colors, so that's the best I can do. Okay. So what's the actual schedule? Well, the schedule is at time T1, you should have committee C1 meet, and also committee C3, and also committee C5. Okay. At time T2, you should have committee C2 and C4 meet. And finally, at time t3, you should have committee C7 and C6 meet. Okay, so this is a schedule where all of the committees have a time slot and there is no conflict, and this is the fewest possible number of meeting times needed to have all of these committees meet. Okay, so that's the end of this example, but I want to mention some things which are important. The first thing I want to mention is that I forgot to say Harriet, which isn't actually important, but you know, that's her name. Okay, so H stands for Harriet. That's not important at all. But what is important is when I found the coloring, it looked like I was doing the greedy coloring algorithm, which I sort of was. But as we know, that doesn't always give you the best, most efficient answer. Okay, so when you're coloring these graphs, you have to make sure that you found the most efficient way of doing it. And like I've said, there's no algorithm which always gives you the most efficient way. It just so happens that what I did gave me the most efficient way of doing it, but you need to make sure that you find the most efficient way however you can. It's usually just trial and error. Okay, like I randomly sort of started coloring them in order. I got a 3 coloring, and then I know that 3 is the best because there's a clique of size 3 right there. Okay, but for the problems you might get, it might not be obvious what the best coloring is, what the most efficient coloring, so you need to actually put thought into this. Okay, that's all I wanted to say. That's the end of the note, and that's the end of this video.